3.1, we talk about duality. Okay, in Chinese we call that 导数. Okay, so it's a bilingual math class here. Okay, so do you guys remember the definition for duality of a function f? Do you guys remember that from 2.8? Right? Anyone can tell me?
F over h.
X plus h minus what?
Fx.
F of x over
H.
Over h. Yeah. So it's the limit of this quotient. Okay. That's the definition for the duality of the function f. Okay. So this symbol here stands for duality. It's called f prime. Okay. Okay. Now today we're gonna derive some formula for duality. We start with the most simple function, which is the constant function, 常函数. Okay, constant function. If f of x is equal to c, c here is a constant, such as 5. Now let's use the definition of the duality to calculate duality of a constant function. Okay, by definition, it's the limit of this quotient. Now, because it's a constant function, f of x plus h and f of x over here both are c, right? They are c. So it will be c here and c here, and you're subtracting over here and then over h. Now the limit over here, now if you simplify this, and that will be 0 over here. The limit of 0 is 0. The limit of a constant is a constant itself. Okay? So we found the formula. So if f of x is equal to c, then f prime of x is equal to 0. In other words, if you have a constant function, the duality of a constant function is 0. Okay? Duality of a constant is 0. Now notice that in chapter 2, we talk about different notation for duality. So you can have f prime of x or y prime. Okay? So y is equal to c. Y prime is the duality of this with respect to x, and that will be equal to 0. Okay. Another notation is this notation. The d dx over here, this part right here, is called differential operator, which means that you differentiate this y with respect to x right here. Okay. So over here, these three are different symbols represent the same thing. Okay. So if y equals c, then dy dx, differentiate y with respect to x, that will be equal to 0. Any question? Now let's try to understand this by looking at the graph of a constant function. What's the graph of a constant function? It's a horizontal line, right? So passing C on the y-axis, so it's a horizontal line. Now we learned that duality corresponds to the slope of the curve, right? What's the slope of this curve? What's the slope for a horizontal line?
0.
It's equal to 0, right? Good. So y prime will be equal to 0. So looking at the graph of a constant function, okay, you see the slope equal to 0, so y prime is equal to 0. So the duality of a constant function is 0. Okay? Okay. Now that will help you remember the duality of a constant is equal to 0. Now another formula we want to derive here is the duality for power function. So x to the n power, okay? So start with this function, f of x equal to x to the first power. Okay, let's use a definition. So it's the limit of, let's write down the definition one more time. F of x plus h okay, minus f of x over h. It's the limit of this quotient over here, right? So what is f of x plus h in this case?
S plus H.
X plus h, right? Okay, so x plus h. What is f of x in this case? Is f, right? Yes. Now simplify over here. So that will be limit of h over h, okay? H over h here it is 1. And the limit of 1 is equal to 1 itself. So we found that the derivative of this function, x, is equal to 1. Now let's try to visualize it, okay? So we graph this function, f of x equal to x, okay? Which is a straight line passing the origin with the slope equal to 1. And we found that the derivative of this function is equal to 1. As you can see from the graph right here, the slope for this straight line right here is equal to 1. So y prime is equal to 1. Because the first derivative corresponds to the slope. Okay. So yeah, so it helps you visualize it. Okay, the slope. Okay, now what about x squared? For x squared over here, we use the definition. So it's the limit of this quotient. Now f of x plus h, we substitute this x plus h into this x right here. We replace this x by x plus h. So the x plus h squared, and then minus here is x squared, and then over h. Now how do we do this? So over here we would like to, there are two ways to do it. One way is to factor the numerator by different the 2 square formula. Another way is to expand this perfect square. So I'm going to expand this perfect square over here in this case, okay? So that will be, everyone tell me, will be x squared plus what?
2xh plus h squared.
Good job. Okay, thank you. And then here minus x squared and then over h. Now when you simplify this, that will become 2xh plus h squared over h. And when we divide out this h, right? So this h over here is a common factor, so we can divide out up and down. That will get this limit of 2x plus h. Okay. Now over here, you see that the variable that is changing over here is the h. Okay, h is approaching the 0. The x over here is regarding as a temporary constant. So in this case, in this limit, the x doesn't change. So it's a temporary constant. So we will substitute h to be 0 over here to find the limit. So that will be equal to 2x. Okay. So we found that the derivative of this function x squared is equal to 2x. Okay. Similarly, we can find the derivative for x cubed. So it's the limit of this quotient. So f of x plus h is what? X plus h cubed, right? Okay. You replace the x here, replace this x over here by x plus h. So you have x plus h cubed, okay. And then minus x cubed over h. Okay, all right, so how do you simplify to find this limit? Now, if you do a direct substitution, you get 0 over 0, right? So it's an indeterminate form. So to get out of that, one way to do that is to factor this right? And then we can divide out the common factor h. Okay. Another way is to expand this perfect cube. Which way you like? Remember, it's a free country. Okay.
Expand the perfect cube.
Perfect cube? Okay,
Yep.
let's expand the perfect cube. Okay. Did I mention that to you about the Pascal triangle, the pattern to expand perfect cube, etc.?
Yes, we did go over it.
Oh, okay, that's good. The coefficient for the perfect cube here will be 1, 3, 3, 1. Okay, remember you have the 1, 1, and then 1, 2, 1. The Pascal triangle. Okay, so okay, so Pascal triangle go like this. So if you have x plus okay, so you have this x plus hq, then the coefficient for the term will be like this. Okay, 1, 3, 3, 1. So 1 here is for x cubed, 3 here will be x square h, and then 3 here will be x h squared plus 1 h cubed. So those are the coefficients for each term right here. Okay, and you see the pattern. The pattern here is the exponent on x here go down by 1 every time, and then exponent on h here increase by 1. Okay. Okay, so x cubed plus 3x squared h plus 3xh squared plus h cubed. So expand the perfect cube. Okay. Now minus this x cubed over h. So that we subtract out over here. Now we can divide out this h. Okay, up and down. Okay. That is going to give me. Now you see that in this limit, x is regarded as a temporary constant. H is changing, so we can do a direct substitution. So substitute the h to be 0 over here. Okay, and we got 3x squared. Okay, all right. Okay, now let's list them. Okay, so for x to the first power, when we differentiate, the derivative is what? Do you guys remember?
1.
1, right? Yeah, you got it. It's 1. Okay, it's 1. And then for x squared, what's the derivative?
2x.
Yes, 2x. Okay. And then for x cubed, the derivative is 3x squared, 3x squared. Okay. And then, guess if we do x to the 4th power, what will be the derivative?
4x cubed.
4x cubed, yeah.
X cubed, yeah. So it is actually proven. You can use the definition, okay, of derivative to prove it. Okay. So actually, in general, by the proof in actually section 3.6, which we are having later on in the future, okay, we have the power rule. Okay, so it is actually proven. So if we have x to the n power, when you differentiate that with respect to x, what will be the derivative? Yes. What should I put here as a derivative? According to the pattern that you have over here, what will be the derivative of x to the n?
Would it be nx to the n minus 1?
Yes, we got it. Okay. And then x to the n minus 1 power, right? Okay, so you see that when we differentiate x to the n power, this exponent here drop to the front, become the coefficient, and the exponent on this x here is going to go down by 1. Okay, this is proven. Okay, it's a power rule. It's proven. Okay, not proved by example, but by the proof in section 3.6. Okay, So in another word, when we differentiate x to the n with respect to x. So you can try to get used to this symbol here. This is called the differential operator. So that means you differentiate this with respect to x. Okay. So when we differentiate x to the n with respect to x, we'll get n times x to the n minus 1 power. Okay, where n is any real number. So not just integer like 1, 2, 3, 4, etc. Could be any real number. Could be fraction. Could be 1/2. Could be 0.7. Could be any real number. Could be pi or any real number. Okay. All right. Any question? All right. Okay. Okay. Now let's practice on this. Okay. So if y is equal to t to the 4 power, then what is dy dt? Now remember, this d dt here means it's a differential operator, which means you differentiate this y with respect to t. So what's the derivative of this y with respect to t? If y equals t to the 4 power. Anyone?
Is it just 4t cubed?
Yes, you got it. Okay. So that will be 4t cubed. Okay. Right, next one. If you have x to the 100 power, okay, what's the derivative of this with respect to x?
100x to the 99?
Yes, 100 and then x to the 99 power. Okay, good job. Okay. Okay, the next one. If f of x equals 1 over x squared, let's rewrite this in power form. So this is x to the what power?
-2?
Yes, negative second power. Yes, we got it. So according to the power rule, remember this could be any real number. Okay. So according to the power rule, this exponent will drop to the front. So we have -2 over here. And then x to the what power?
-3?
-3. Yes, you decrease this by 1, right? So subtracting 1, so that's -2. And let's rewrite this without negative exponent. So that's -2 over x cubed over here. Question? Okay, the next one. If y equal to the cube root of x to the second power, okay, let's rewrite this in a power form, okay? So let's say, so this is x to the what power? Do you guys remember?
2/3?
To the, you got it, okay? So x to the 2 over 3 to the power, okay? Now, notice that cube root of x squared, what happened over here is this 3 over here is the index of the root. And that will go over here. So that's the index of the root. Okay, so go over here in the denominator in this exponent. This power over here on this x over here, this 2 will go up here. Okay. The sum applied to this. When you have cube root of x and then we raised it to the second power, you have the sum. This is also x to the 2 over the power. So now we rewrite this in power form. We can use the power rule to differentiate this. Okay. So according to the power rule, what do we get? So this exponent will drop to the front, right? So we get 2 over 3. And then we will have x to the what power?
-1/3?
Yes, you got it. Okay, it's negative 1/3. Because this is going to go down by 1, so you subtract 1, so it's negative 1/3. Okay, now let's rewrite this without negative exponent. So this will be 2 over 3, and then x to the 1/3 in the denominator. Or another way to write this, you use the radical sign. So it's 3 here. X to the 1/3 power is the cube root of x. Okay, so that's a different way to write this. So that's the power rule. Okay. Now we're going to talk about this. This is constant multiple rule. When you differentiate a constant times a differentiable function, okay, then what happens here is you can bring this constant in front of the derivative. So that will be this constant multiplied with the derivative of the function. Okay. Okay, let's try this example together. So if f of x equal to 3x to the 5th power, what will be f prime of x? So that will have this constant multiple, right? So this constant multiple 3 will drop to the front.
15.
Yes, you got it. And then we're going to differentiate x to the 5th power, right? So bring this constant to the front, and then differentiate x to the 5th power with respect to x, okay? We already know from the power rule, okay, when we differentiate x to the 5th power with respect to x, we got 5x to the 4th power, right? Okay, and you say this is 15, and then x to the 4th power. You got it, okay? So from here to this. Now, what about this? This one here has a negative sign in front. You should think about that like you're having a constant multiple. It's like multiply with negative 1. So you can bring it in front, right? So that will be negative. So will be negative of this. And dx dx is equal to 1. The derivative of x with respect to x is 1, right? 1. Yeah, it's 1. Okay. Okay. So another rule, there's so many rules. So another rule is a sum rule and difference rule for derivative. So if we differentiate the sum of two differentiable functions, then it's the sum of the derivatives. And the derivative of the difference is the difference of the derivative. Okay? So if you look at this example, okay, if you look at this example, okay, right here, we have the sum here, difference here, right? And sum here, and the constant multiple here and here, right? Okay. So sometimes in the book, they ask you to write down what rule did you use in each step, okay? So in the beginning, so I think we should justify, right? But after a while, you get used to, you know that already, then you don't have to. But in the beginning, let's justify every step right now, okay? You see it. So the first one over here we use is this, the power rule. So this will be what? 8x to the 7, right? And then the 12 over here is a constant multiple. So we have this constant multiple in front. And then we'll differentiate x cubed. What's the derivative x cubed with respect to x? We use the power rule, so that will be what?
3x squared.
Yes, you got it. So that will be 3x squared. Okay. And then minus the negative 6 over here is a constant multiple. So negative 6. The derivative of x with respect to x is 1, right? Okay. So that is 1. Okay. What about 5? What's the derivative of 5?
0.
It's 0. Yes, you got it. the derivative of a constant is equal to 0, remember. Okay, so that will be 0. So derivative of this constant is 0. Derivative of a constant is 0. Okay. So over here, the rule that we use here is the power rule, constant multiple rule. Power rule here, constant multiple rule. And we also use the sum rule and the difference rule and the sum rule right here. Okay. Okay. Now then, we need to simplify it. Okay. When possible, we simplify. Simplify when we got this result right here. Okay. Okay. The next one. Over here, we have this position function. So given that, where t is in second and s over here is in centimeter. Okay, we find the velocity function. So vt. Now remember, when you're given the position function, and this one object travel along a straight line, the velocity function corresponds to the first derivative of this function. Derivative of this function with respect to t. So we can use the constant multiple rule, power rule, difference rule, sum rule, etc. Okay, to find the derivative of this, right? So what does it equal to, everyone? What's the derivative of this? 2 times what?
3t squared.
3t squared, which is going to be 6
6t squared.
squared. Yes. And then the next one, 5 times 2t.
And t.
10t.
Yeah, you got it. And then the derivative is 3. 3. Yes, you got it. So plus 3. And the derivative of 4 is what?
0.
0. Yes. So that would be a derivative. So the derivative of the position function here is the velocity function. So that's the velocity function here. And what about the acceleration function? How is acceleration is the derivative of the velocity. So it's the second derivative of the position function. So acceleration corresponds to the second derivative of the position function, which is the derivative of the velocity function. So we're going to differentiate this one more time with respect to t. So that will be equal to what? 12t, right? And then minus
10.
10, you got it. And you can substitute t to be different number. So for example, when t equal to 2 seconds, okay, then the acceleration at that time, we can just substitute 2 into this t here. So we get 12 times 2. And then minus 10. So that will be 14. And the unit here will be centimeter per second square. Now, the next one over here is this. We're given this curve here. We try to find points on this curve where the tangent line is horizontal. So how do we do it? When we talk about tangent line is horizontal, that means the slope of the tangent line is equal to 0. Okay? So, which means the first derivative will be equal to 0. Okay? So that means the derivative y prime over here is equal to 0. So we'll first differentiate this. So we find y prime, and then we respect that equal to 0 to find those points. Okay. So y prime is equal to what? Everyone? Differentiate this with respect to x. What do we get?
4x.
4x cubed minus
20.
12x.
6 times 2x, which is going to be 12x. Yeah, you got it. Okay. Okay, now we're going to set this equal to 0, right? We're going to set that equal to 0 to find those points on this curve that the tangent line will be horizontal. And then to find those points, we need to solve for x. Okay, let's solve for x over here. We want to use the zero factor property, so we want to factor this side. Okay, so we take out the common factor for x, and we have x squared minus 3 here as the other factor equal to 0. So to make this product equal to 0, we can have 4x equal to 0 or x squared minus 3 equal to 0. So from 4x equal to 0, we will get x equal to 0, right? So we get either 4x equal to 0 or x squared minus 3 equal to 0. And here we get x equal to 0. And from this, we get x squared equal to 3. X squared equal to 3, what does x equal to? You take square root, right? You take square on both sides. So x equal to positive or
Square root of 3.
square root of 3, yes. Now, there are two roots, okay? Both positive or negative square root of 3, when you square them, you get positive 3. So don't forget you have two roots, positive and negative root. Now we're going to find those points. Here are the x coordinate for those points. To find the y coordinate, we need to plug this x into the function to find y, right? So I'm going to plug x equal to 0 into the function. Okay, now what's that function? It's this function right here. So plug in x equal to 0. So y will be equal to 4. And if you plug in x equal to positive or negative square root of 3, well, we're going to get y is equal to, this is actually an even function. Because this is an even function, you see the exponent on the x here, those are even. And so the result, if you plug in positive and negative square root of 3, the result will turn out to be the same. So this will be equal to 9 minus 18 plus 4, which is equal to negative 5. Okay, so we can write a sentence here. So the answer over here will be at all these 3 points, the tangent lines are horizontal. Okay, all right, are you guys good? Okay, now the next one over here. Okay, we're going to talk about this lecture number E. Okay, if you can remember the first couple digits of E is 2.718 and dot dot dot. Okay, so if it is actually an irrational number like pi, the digit here continue forever and there's no pattern of repeating. So it's between 2 and 3, about 2.7. Somewhere over here, it's about 2.7. Okay, the definition of E, okay, on this in our book on page 118, say they define E this way. Okay, E is a number such that when you take this limit, okay, when you take limit of this quotient, that's equal to 1. Now this quotient here has something to do with the slope of exponential function. Okay, so e to the x. Okay, so when you have e to the x over here, okay, then what happened over here? This corresponds to the derivative of this function when x equal to 0, which corresponds to the slope of this tangent line right here. So e to the x is the one that the slope of the tangent at this point is equal to 1. So if you try 2 to the x, 3 to the x, then the slope of the tangent is not 1. Okay, so let's try to find the derivative of e to the x. Okay, let's try to find the derivative e to the x. Let's use the definition to find the derivative e to the x. Okay, so that's the limit of this quotient, f of x plus h minus f of x over h, right? Okay, which is going to be e to the x plus h. Well, remember, we replace the x here by x plus h, right? And then here's e to the x over h. So notice e to the x plus h is e to the x times e to the h. So this part over here, so we can take out this common factor e to the x over here, okay? And now notice that in this limit here, h is changing. X is a temporary constant. So we can bring out e to the x over here. It's a temporary constant in front of this. So we have this e to the x. And take the limit of this quotient right here. What is this limit?
1.
Yeah, it is 1. Yeah, this limit over here, it is 1 by the definition, right? By the definition. So 1 times e to the x is e to the x. So we got e to the x. Okay, so that's equal to e to the x. We just discovered that, okay? So we just discovered that the duality of e to the x by definition, and we got e to the x. Yeah. So e to the x, the duality, when you differentiate that with respect to x, is e to the x. So that was this math joke, okay? So the whole basket, there's a true basket full of truths. And then someone come on and say, I'm going to differentiate you, all of you. And then this guy will say, he would just stand in there and say, I'm not afraid, I'm e to the x. Okay? So e to the x is the one not afraid to be differentiated. So no matter how many times you differentiate that, it remains e to the x itself. Okay, now let's try this one over here. Okay, let's do this example. E to the x minus x. Let's take the first duality. Okay, differentiate this with respect to x. What do we get, everyone? The duality of e to the x is e to the x itself. So we got e to the x over here. What's the duality of negative x? Minus 1, right? Negative 1. Okay, now we differentiate this one more time. Differentiate this, e to the x, we got what? E to the x, right? Okay. Now we differentiate this negative 1. What do we get?
0.
So, yeah, so now we just get e to the x. Now from here on, if I differentiate this one more time, what do I get?
E to the x.
E to the x itself. So if you continue on to differentiate, you always get that e to the x. Okay. Okay, this one here you might need it for homework. Okay. So y equal to e to x, you find points on the graph where the tangent line is parallel to this line over here. Okay. So first of all, when you say this, the tangent line is parallel to this. When two lines are parallel, they will have the same slope, which means y prime will be equal to 2, right? This 2 over here is the slope. So y prime will be equal to 2, right here, okay? So we're going to differentiate this function, and then we're going to set y prime equal to 2 to find those points, okay? Now we're going to differentiate this function right now, okay? So we got y prime is the duality e to the x is e to the x itself, so it's e to the x. And we're going to set that equal to 2. Okay. And now we get e to the x is equal to 2. Okay. To solve for x, what is x equal to? Anyone? So x is equal to ln of 2, right? If e to the x equal to 2, then x will be equal to ln of 2, base e log of 2. right? Okay. Now, after that, we're going to plug this x in and then just solve for y. Okay. So we're going to plug x equal to Ln of 2. We get y is e to the Ln of 2. What's e to the Ln of 2? Anyone? Remember this base e exponential function and base e log? They are inverse function. So when you compose this way, it will cancel. And yeah, that will give you 2. You got it. Okay. So y equal 2. So we say, now we find that point. So at this point, where x coordinate is Ln of 2, y coordinate is 2, the tangent line is parallel to this line, y equal to x. Okay, let's summarize what we have learned today. Okay, what we have discovered today. So the derivative of constant is what? Everyone?
0.
It's going to be 0. Okay, good. So that will be 0. Derivative x to the n is
And x to the n
n times x to the
n minus
n minus 1, right? Okay. E to the x, the derivative is
e to the x.
e to the x itself. So we're not afraid to be differentiated, right? And then constant multiple rule. Then this constant will bring to the front, and you just, it's a constant times the derivative of the function.
This is a constant.
Don't confuse this with x to the 80 power. This is a 2. This is 2 to the 80 power. So
Just 0.
yeah, it is a constant. So derivative of a constant is going to be 0. Yes, you got it. So in your homework, don't confuse this with the power rule. Okay? So derivative of a constant is 0. Okay. Now another homework help that I want to give you here is in our book, x, y, z, or t represent variable, and they use a, b, c, k, m, n represent constant. Okay. So like y equal to mx plus b, m and b here represent constant. The x over here is the variable. X and y are the variables. Okay. So if you differentiate this with respect to x, what will be the derivative over here?
M.
Yes, you got it. The derivative will be m. Okay. So for example, y equal 5x plus 3, the derivative of this will be 5.
Okay.
Yeah, you got it. Okay, the last part here, I draw an animation. I draw a cartoon. Okay, I make up a cartoon with this. I'm going to tell you the story. Okay. So, so one day, okay. So one day, e to the x. Okay, so this is e to the x right here. E to the x over here. Okay, and this constant function c. This constant function here, c over here. They are walking down the street. Okay, and far away, they saw differential operator. Remember the differential operator, d dx. Okay, so this differential operator was coming their way, so coming toward them. Okay, so c is c over here. This constant function. His face turned pale and started to run away. And then e to the x and asked, "Why are you so scared of d dx?" And c answered, "If he gets me, I will have nothing left." And then e to the x says, "I have nothing to worry about. I'm e to the x." Do you like my drawing? I designed this. Okay?
Oh,
I love it. That was a great story.
Because the derivative of c here is what? Derivative c is equal to what? Equal to
0.
0.
so we have nothing left, right? Derivative e to the x is what?
E to the
E
x.
to the this it doesn't change. Okay? So I actually decided this drawing. See, when he's not afraid, so his eye is twinkling like this, and then the C has the mouth open. Okay. Okay, so I actually decided this. It's copyright by me.
Okay.
Okay, I didn't make the story, but I make the drawing. I designed the drawing. Okay, all right. So the lesson ended. Let's say goodbye to each other. So I'm gonna stop share. Okay, all right.